Welcome back to Wired for Precision, the podcast where we deep dive into the world of instrumentation, automation, and engineering excellence. I'm your host, Phil, and today we're shining the spotlight on something that often gets overlooked. But without it, your entire system might be working blind. We're talking about signal conditioning, the unsung hero of accurate measurement and control. Let's start from the top. Signal conditioning is the process of manipulating a signal in a way that prepares it for the next stage of processing. Typically, that means converting raw data from sensors into a form that a controller, like a PLC or a data acquisition system, can interpret accurately and reliably. Raw sensor signals are often noisy, low voltage, or nonlinear. Signal conditioning improves them, whether by amplifying, filtering, converting, or isolating the signal, to ensure precision and integrity. There are five major functions signal conditioning devices perform, and understanding them is key to designing robust systems. 1. Amplification boosts low-level signals, like from a thermocouple, to measurable levels, for example, 1 to 5 volts or 4 to 20 milliamps. 2. Filtering removes electrical noise and high-frequency interference, especially important in industrial environments full of EMI. 3. Isolation protects the system and personnel from high voltage spikes. Optical or transformer isolation prevents ground loops. 4. Linearization corrects nonlinear sensor outputs. For example, converting a thermocouple's curved response into a linear temperature scale. 5. Signal conversion changes one type of signal into another, such as voltage to current, analog to digital, or vice versa. Each of these plays a role in ensuring the signal reflects the true process variable, nothing more, nothing less. Traditionally, signal conditioning was purely analog. Think op amps, resistors, capacitors, and isolation transformers. Today, however, digital signal conditioning is gaining ground. It includes digital filtering, compensation algorithms, and even embedded microcontrollers. Some smart transmitters now handle signal conditioning internally, applying compensation curves, diagnostics, and digital communication, like HART or Modbus, right inside the sensor head. So when do you go analog and when digital? The answer depends on speed, resolution, environment, and cost. Let's bring it down to the plant floor. Here are some places where signal conditioning is quietly doing the heavy lifting. Temperature measurement. Thermocouples generate millivolt signals that need amplification, cold junction compensation, and linearization. Load cells and strain gauges. These require high-precision bridge amplifiers and noise rejection to be useful. Pressure transmitters often have internal signal conditioning that converts diaphragm movement into stable 4 to 20 milliamps or digital outputs. Flow meters use conditioning to deal with pulsed outputs or variable frequency signals. Without proper conditioning, your control system might misread the signal, leading to incorrect actions, alarms, or data logs. As control systems evolve, so does signal conditioning. With modern PLCs and SCADA systems, you often need to convert legacy analog signals into digital formats that support Ethernet IP, Profibus, or OPC-UA. In IoT applications, signal conditioning is crucial for reliable remote data, especially when dealing with wireless sensors, edge devices, and cloud monitoring. You need clean, isolated, accurate signals for smart decisions. And now, many I/O modules come with built-in signal conditioning, reducing the need for external modules, but it still requires proper setup, calibration, and validation. So, how do you ensure your signal conditioning strategy is solid? Best practices include selecting signal conditioners with matching input-output ranges, ensuring proper shielding and grounding to prevent EMI, using redundant isolation for safety-critical systems, periodic calibration and verification of conditioning modules, keeping documentation of all signal paths and scaling factors. Looking ahead, we're seeing a shift towards software-defined signal conditioning, where FPGAs or digital cores can be updated remotely. AI-driven diagnostics are even starting to flag drift or failure in signal paths before they cause downtime. To wrap up, signal conditioning may be hidden behind panels and terminals, but it plays a starring role in accurate, safe, and efficient control. Thanks for tuning in to Wired for Precision. If you found this episode valuable, make sure to subscribe, leave a review, and share it with your fellow engineers and technicians. And if there's a topic you'd love us to dive into next, let me know in the comments or message me directly. Until next time, keep your signals clean, your systems tuned, and your measurements precise.